Hello, and welcome to my After Cafe talk. My name is Jordan Meillet. I am a staff scientist in the molecular spectroscopy team in the Material Research Institute at Penn State University. Today, I will be talking about controlled temperature and our atmosphere for material characterization. Often, material characterization are carried out under pristine or static condition, which does not always reflect the chemistry or dynamic at play under operation condition. It opens the curiosity of what happens when the material is put in use and how it evolves while being operated. For this reason, there is a requirement to characterize the evolution of material and the chemistry happening when the material is exposed to the thermal or atmospheric condition it is intended to be used. These practical concepts have been introduced in the scientific field of biology and catalysis, where the static analysis is referred as ex situ and the dynamic characterization is referred as in situ. The picture presented in this slide shows a snapshot of a flower in two different states. The first one corresponds to the flower before it bloomed, and the second after blooming. While it could be imagined how the flower went from the pre-blooming state to the fully bloomed state, without further information, it is impossible to know with certainty the process undergoing during the blooming of the flower. For this reason, a more dynamic vision of the process, in this case a video, gives further information on the blooming process of the flower. This would represent if we were talking about material characterization to an in situ or dynamic characterization. While performing advanced characterization of material under controlled atmosphere and or temperature can bring more clarity into the scientific understanding of the material behavior, several points need to be addressed. First of all, the safety concern of the measurement. Since external energy is introduced into the system, it is extremely important to plan carefully the experiment and know what to expect. One practical example will be the production of nickel carbonyl, a compound presenting acute toxicity that will be formed by the reaction of nickel metal and carbon monoxide. The second point to address is the reproducibility. Introducing more parameters into the characterization technique involves an increasing amount of possible error. That's why it is extremely important to run controlled experiments to understand what is coming from the material and what is intrinsic to the system. The third point to consider is planning. Since the measurement is more complex than one-point characterization, planning the experiment carefully with an idea to the potential outcome is important. Lastly, the cost of such experiment. As discussed earlier, the complexity of the experiment, the setup, and experimental design ultimately mean an increase of the analysis cost. Now that we have defined the basis of what is implied by atmosphere and temperature characterization, we can go more into detail onto a non-exhaustive list of accessories and practical examples of in situ measurements performed at the material characterization lab. One of the techniques where controlled temperature and atmosphere can be performed is transmission electron microscopy. This technique is supported by our staff member Jennifer Gray and Kay Wang. At MCL, we dispose of three main accessories from protochips allowing to perform in situ measurements. The first one, fusion, allows to perform thermal and electrical measurements with a maximum temperature of 1200 Celsius and a max current of 100 milliamp. The second accessory, named Poseidon, allows to handle liquid sample with the ability to perform static or flow experiments, as well as in situ electrochemistry. The last device, named Atmosphere, allows the introduction of gas phase into the system while simultaneously apply temperature and or pressure. Now I will give you some examples of analysis performed at MCL. The first example was carried out with the research group of Professor Jingjing Li using the Fusion TEM holder. They were interested in the thermal behavior of aluminum-copper welding interface. In the picture, we can clearly see the dynamic of the welding interface when temperature is introduced into the system. We can see the magnesium present in the aluminum side progressing towards the interface to form a junction between the aluminum and copper. The second example was also carried out using the Fusion TEM holder. It was made in collaboration of the group of Professor Copalan on a calcium ruthenium oxide material. On those pictures, we can see that there is two separated polar domain, and applying an electric biasing with this TEM holder induce a 90-degree ferroelastic domain switching. The last example was carried out with the research group of Professor Kelly using the TEM holder Poseidon. It was a study of rotavirus in solution. While most of the analysis of rotavirus are made using a cryo-TEM holder, this example shows the dynamic that happens when the rotavirus is present into a solution. This study allowed to see some conformation difference in the rotavirus domain using in situ liquid TEM. Another technique where controlled temperature and/or atmosphere can be performed is X-ray scattering. This technique is supported by our staff member Nicole Wanderling. We can see in this slide the different apparatus present at MCL along with the different accessories that are used to do in situ measurement. We can see that the temperature range where the analysis can be done goes from liquid nitrogen temperature up to 1600 Celsius. We can also see that analysis can be performed under vacuum, air, inert environment, and we can also introduce a percentage of humidity to see the behavior of the material under wet conditions. An example of the use of in situ accessory for X-ray scattering was carried out in collaboration of the group of Professor Maria. In this example, the high temperature X-ray scattering of termite was studied. Termites are inorganic energetic material that produce an exothermic reduction-oxidation reaction. The main question for this study was, is the termite redox reaction really so simple? What could be learned from this study is the formation of an intermetallic magnesium-copper peak at approximately 500 Celsius. We can also see the complete loss of the magnesium peak and the formation of this intermetallic mixture at 525 Celsius. And we can also see when we increase the temperature up to 650 degrees centigrade, the loss of all intermetallic peak. Combination of all this information allows to evidence the presence of a transient liquid intermetallic domain, and this intermetallic formation is coupled with the redox reaction. Another technique that could be used in combination of controlled atmosphere and/or temperature is Raman spectroscopy. This technique is supported by our staff member Maxwell Wetherington. In this slide, you can see all the instruments present at the Material Characterization Lab with laser ranging from 488 nanometer up to 1064 nanometer. Those instruments can be coupled with this LINCAM FTIR 600 temperature environmental stage. This stage allows to introduce temperature ranging from liquid nitrogen up to 600 Celsius. It also allows to introduce a gas such as argon in order to keep your material under inert condition. I will give you an example of the application of in situ spectroscopy using Raman. This example was carried out in the group of Professor Robinson on the confinement of heteroepitaxy. The group was interested into the behavior of 2D gallium intercalated between silicon carbide and graphene. In order to understand the behavior of 2D gallium into this material, the material was warmed up to 623 Kelvin. What we can see is the vanishing of the signal for 2D gallium with a metal low frequency feature, likely indicating the transition into a liquid state happening at 600 Kelvin. When the same material is cooled down, we can see an increase of the full width half max of this metal low frequency feature, which indicates that the 2D gallium is likely in an ordered phase below 285 Kelvin. It is in a disordered phase between 285 and 600 Kelvin, and more likely in a liquid phase above 600 Kelvin. Another technique where controlled atmosphere and/or temperature can be performed is Fourier transform infrared spectroscopy. This technique is supported by our staff member Tawanda Zimutsi. In this picture, we can see all the accessories present at the Material Characterization Lab, allowing to analyze sample from the liquid state to the solid state. We can also look at the sample at different temperature and in different geometry configuration. An example of in situ FTIR spectroscopy was carried out by the group of Professor Wang on a ferroelectric polymer. By applying a change in temperature, we could see a change of the conformation of the polymer. This analysis confirmed the piezoelectric behavior of the material under a thermal stimulus. Another example of in situ FTIR spectroscopy was carried out in the group of Professor Ryu with platinum supported Anseria. In this example, what we can see is the dosing of this platinum Ceria material at room temperature. We can observe the presence of carbon monoxide in the gas phase, along with the presence of carbon monoxide binded to platinum 2. When this material, platinum supported Anseria, is reacted with a mixture of carbon monoxide and oxygen at 140 Celsius, we can see the presence of platinum in two different oxidation states. We can see the bond corresponding to platinum at the oxidation state +2 with carbon monoxide coordinated to it, along with the presence of platinum nanoparticle. This example shows the behavior of the material under gaseous condition. The main question will be what can be further done using FTIR spectroscopy in the in situ world. Several angles are possible. The first one is using, for example, small molecule adsorb on the material in order to identify, for example, with carbon monoxide, the oxidation state of the metal, or with a small molecule like pyridine, the acidity of the material. Another possibility would be to do step scan, transient or pump probe experiment. These techniques allows to see events happening at really fast scale. Another angle will be using isotopic labeling in order to get further information into the dynamic of the surface chemistry of the material. By using a different isotopic label gas, we can see a shift in the FTIR signal indicating a change of behavior. The last angle that can be tackled using FTIR spectroscopy will be to create in situ cell in order to address a maximum amount of scientific questions. With this vision in mind, I would like to introduce the in situ satellite at the Chemical and Biomedical Engineering building from MCL that would allow to analyze material at different temperatures from liquid nitrogen up to 600 Celsius using a wide range of gas ranging from vacuum, nitrogen, carbon monoxide, hydrogen, and synthetic air. We'll be able to control the flow of those gases using mass flow controller and also allowed to introduce small molecule by injection in a syringe pump. The future project will include the production of step scan FTIR spectroscopy, isotopic labeling, and any experimental design required for your research. We can talk about that. Thank you very much for watching this video.